Hi, this video is a kind of silly example of a case of conservation of angular momentum when we have what we call deformable systems. And you see this all the time if you watch winter sports like figure skating when all of the sports in the world aren't shut down. But normally around this time of year, there'd be national and international figure skating championships, and one of the things that you always see at the end are the figure skaters. They'll go into a twirl, and then they'll pull their arms in tight, and then at the end, they'll throw their arms apart to stop. Now, there's some style points that go along with that, but what they're really doing is changing their rotational inertia. So normally when we think about a conservation of momentum problem, we're thinking about like collisions, because conservation of momentum gives us a really powerful way of looking at problems where we can't look at well-defined forces or well-defined torques for the case of angular momentum. Well, with deformable systems, we only need one object. But what happens is if our rotational inertia can change, then our angular velocity can change in order to conserve the angular momentum. So when that figure skater brings in their arms, they start spinning faster because they have some angular momentum, and their rotational inertia gets smaller as more mass gets closer to the center. In flinging their arms and legs wide, their rotational inertia skyrockets, slowing their angular velocity, which makes it a lot easier for them to apply the toe brakes on their skates to actually stop them. So let's get silly with a little bit of an example. So all of the sort of classic pictures of UFOs from the 50s movies, they were spinning around for some reason like a frisbee. It helps frisbees fly, spacecraft, not so much. There are a lot of reasons why having a really rapidly spinning spacecraft would be really bad for particularly human passengers. And aliens always want to kidnap Elvis, because why not? So let's say that some aliens are trying to make some room on their spaceship for Elvis. So the spaceship's initially rotating at 64 radians per second, and it ends by rotating at 53 radians per second. What's going to be the change in rotational inertia that they'll have to achieve in order to make that happen? Well, if the initial inertia times the initial angular velocity is the final inertia times the final angular velocity, then the ratio of initial inertia to final inertia will be the same as the ratio of the final velocity to the initial velocity. And 53 radians per second over 64 radians per second gives us a ratio of 0.83. So that means that the initial inertia is smaller than our final inertia. So how can you do that? Well, if you think about a spaceship as being like a room, you can scoot all of the chairs closer to the wall, further away from the center, inertia goes up, everything's going to slow down on its own. Bon voyage, King. I'll see you later.